Okay, so continuous random variables, frequently asked questions. Every problem has a unique distribution. What we're going to do, just like we did with the discrete, is we're going to look through the most common ones. We use extensive calculus in this section, or these groups of sections. No. I mean, intuitively and conceptually, the importance of, why calculus is relevant to this area, we'll look at that somewhat. But again, in this case, since we're looking at most common distributions, we're also going to be using tables associated with these different distributions. And those tables, somebody else has already done the integration for you. And they've already done the proofs associated with the expected values and the variances. So we're basically going to, again, I want to try and give you some sense of the weeds in these topics, but you're not going to go digging so far deep into them. Once you kind of stand at that higher level, see in the forest, understanding why this is relevant, why it's important in different engineering fields. What's the toughest part? The toughest part is similar to the discrete. It's that same, you're a reliability engineer, and your manager has asked you to do a study to determine the different probabilities associated with the life length of the products that you're creating. And so fitting that distribution, again, doing a study and understanding what all that's about and giving some reliable information upon which managers or however can make decisions, make changes to how things are being made, that's the hard part of this. So again, we study some things just to give you some tools to work with, get you started on understanding these different topics for your future careers. Okay, moving on. So we're going to go first into the continuous uniform distribution as the one of the most common distributions that come up. And what is the continuous uniform? Well, it's similar here. Remember that in the discrete we said that the roll of the die was the one. Probability was always the same, no matter whether you rolled a 1 or a 5 or a 6. It always had a 1/6 probability. So that was in the discrete uniform distribution. So how do you have something, how do you find something similar for a continuous random variable? And that's what this gives. General characteristic, given an interval S, subintervals of length D are equally likely to contain a value for X, no matter where the subinterval lies in S. Let me go right off to the picture, okay? That's not it. Okay, this is the picture I want. No, that's not the picture I want. Come on, picture. Here we go, visually. All right. So we have a random variable X, continuous. You're told that it can lie between A and B. So I could have a random variable that lies between 3 and 7, let's say. So we say, well, again, you're not going to say what's the probability that the random variable takes the value of 3.5 exactly or 4.3 exactly, but we're going to look at subintervals of a certain length. So what we say, 3 and 7, so 7 minus 3 is 4, so 1/4. And now let's say I'm interested in the probability that the random variable falls between 4 and 5. Okay? No, let's say 4 and 6. So that's a distance of 2, or a D value of 2. 4 to 6, right, is 2. And so what's the probability that the random variable falls between 4, C is equal to 4, and 6, which is 4 plus 2, that's just equal to 2 over 4, or 1/2. But what we're going to see is that the reason they call it a uniform distribution is if I had asked you the question of, that was between 4 and 6, I could say 3 and 5. Probability that random variable, so let me say this again. Probability that the random variable falls between 4 and 6 was 1/2. Probability that the random variable falls between 3 and 5 is also 1/2. Probability that the random variable falls between 2 and 4 is 1/2. It's the same probabilities that the random variable is going to fall in that range. I think I've just messed that up. 7 minus 3 is 4. Is that right? So 2, yeah. Okay. So any of those subintervals would have the same probabilities. Okay? And so that's what the continuous uniform does. It gives you this, where it's simply that A and B and the probability along that, within that interval is the probability that you have. So that's what this is saying. This is just mathematical notation that A and B be two given real numbers such that A is less than B, and consider an experiment in which a point X is selected from an interval between A and B in such a way that the probability of X will belong in each subinterval S is proportional to the length of the subinterval. Okay, that's that D. Then X is said to have a uniform probability distribution function described as P of X. So again, one of the things, now P of X equal to 1 over B minus A, back to the, assigning 0 values for probabilities, this is a mathematical function. We're thinking about it over between values of A and B. So you don't just plug in a number, well, the probability of X equal to 3.5 is just equal to 1 over, B minus A for that particular value. No, we're going to work with this. Think about it as a mathematical function that you're working with, and you're going to look at subintervals. Okay. The mean of a uniform distribution, continuous uniform distribution, is, and again, we're not going to go through the proof of this, but you could do it if you wanted to integrate X times 1 over B minus A, integrate from A to B, you would end up having A plus B over 2 as the mean of that distribution. Variance is equal to 1/12 times B minus A squared. So this is your continuous uniform distribution, probability distribution. This is just showing you proof. This is actually a short little proof. If we consider a subinterval of length D that is contained within A and B, then all this is showing is using the definition of a continuous distribution function, showing that the probability that X would fall between C and C plus D is just equal to the probability is equal to D over B minus A. So it doesn't matter where that subinterval is between A and B. You shift it around, as I mentioned earlier. You still have the same probability, D over B minus A. Okay, so here's an example. The failure of a circuit board interrupts work by a computing system until a new board is delivered. The delivery time X is uniformly distributed over an interval from 1 to 5 days. Equally likely that the delivery time would be 1 day, 2 days, 2.5 days, 3.5 days, whatever. It's uniformly distributed. And note that A is equal to 1 and B is equal to 5. What is the probability distribution function, PDF? P of X then is 1 over B minus A, which in this case is 1/4. And 0 elsewhere. What's the average delivery time? Well, we know that that's equal to A plus B over 2, or 3 days in this case. What's the probability of delivery time between 1 to 3 days? Oh, this is just actually what I was just showing you. 1 to 3 days, okay, the D there is 2, and B minus A is 5 minus 1, or 4, so it's a 1/2. Note that that's the same probability associated with that the delivery time will be between 2 and 4 days. also 1/2. So it's the same kind of feel. Which if you're a customer, that's not the best kind of thing you really want. Is you'd hopefully, and this is where the application of the uniform distribution comes into question. You've got to think carefully about, does it fit the problem you're addressing? If you are Geek Squad or at Best Buy, or you are FedEx or something like that, you would hope that the probability of delivery between 1 and 3 days is higher than the probability of delivery between 2 and 4 days. So this doesn't always fit all the scenarios, but just again, we're looking at it. This particular distribution assumes that those probabilities of the same subinterval, 1 to 3 days, 2 to 4 days, they have the same probability. We'll call the cumulative distribution function for a continuous meant integrating from minus infinity to whatever value x you're doing, f of x. So you're integrating that function. And again, we're not going through the proof of this, but you could integrate to find the probability, the cumulative distribution function for a uniformly distributed continuous random variable x. F of x is equal to 0 for all value of x, of course, that are less than a, because that x, there's no chance of the random variable taking any value less than a. It's been stated that way. And then what's the probability that the random variable x, the cumulative distribution then, for x values of x between a and b is just equal to x minus a over b minus a. And then what's the cumulative distribution? Probability that x is greater than b, again, it's the cumulative distribution, which is just going to be totaled up to 1. All right, this is a graphical look at what the continuous distribution function looks like for a uniform distribution. We have a special kind of uniform distribution where a is equal to 0, b is equal to 1. This is This is a frequently used distribution for generating random numbers, seeds for simulation models, and variance played with off of this. In this case, the cumulative distribution function simplifies to be just x for whatever value between x, for a value of x between 0 and 1. The mean of this uniform distribution, standard uniform, would be 1/2, and the variance is just equal to 1/12. Okay, so another example. A bomb is to be dropped along a 1-mile long line that stretches across a practice target zone. The target zone center is at the midpoint of the line. The target will be destroyed if the bomb falls within 1/10 of either side of the center. Excuse me. Find the probability that the target will be destroyed given that the bomb falls at a random location along the line. Okay, so the center zone, the zone center is at the midpoint, or at 0.5 of a mile, or 0.5, half a mile. We're interested in finding the probability that, okay, so it's going to fall within 1/10 of the center. So 1/10 below that would be 4/10. 1/10 above the center is going to be 6/10. So we want to know what's the probability that the random variable is between 4/10 and 6/10. And just using what is the f of the cumulative distribution function for 6/10 is, again, f of the cumulative distribution is just the value of x itself, or 6/10, minus f of 4/10, which is, again, just the value of the 4/10, so therefore is 2/10 or 0.2. So that, again, is the probability that the random variable is between 4/10 and 6/10. Okay, so that wraps up just a brief look at the continuous uniform distribution. In the next recording session, we'll turn our attention to the exponential distribution.